Hi, this is Pradeep and welcome to Code Verify. In this video lesson, we will continue our tutorial on which we were doing heap sort on a given array in part 1. In part 1, we have successfully made the max heap by using the input array. So this was the array and we printed out the final max heap which we wrote from this array. If I run this program and show you the final max heap array, then this was the output of the final array, and I printed the max heap, that is 8674531. So this is the max heap that built in the previous tutorial. So now that we have got the max heap, so now we can actually do this heap sort, because until and unless we had the max heap, we could not have done the heap sort. So now let's move ahead. So now this was from my previous video where I had already constructed the max heap. So this is the tree representation and this is the array representation of that max heap. So now since we are going to sort it, the sorted array is going to look like this. But to reach this step in which all the elements are in ascending order and sorted, we have to do some intermediate steps. Now as you can see from this max heap array, 8 is the maximum element in this entire array. So I'm going to swap 8 with 1, that is the current size index. So we finally got 8 in the position where we wanted it to be. So now we're going to decrease our current size by 1 and also eliminate 8 from this equation. By eliminating 8, our final array also gets reduced by 1, and now the array ranges from index 1 to index 7. And you can see that when we have swapped 1 with 8, the final arrangement that we got, it certainly violates the max heap property. So now we're going to restore the max heap property so that this finally reduced array looks like a max heap array. To do that, we're going to compare 1 with its left and right child. So first we're going to see which child is the greatest. Like here 7 is the greatest, and we're gonna compare 7 with 1, and we see that yes, 7 is greater than 1, which means we're gonna swap 1 with 7. After doing so, the new position of 1 becomes index 3. But now 1 again will see its left child and right child, find the greatest among them, and then compare it with itself. This time 3 is also greater than 1, so again 1 swaps itself with 3. So 1 bubbles down and 3 bubbles up. Now after doing so, we see that finally the max heap property has been restored, in which every root is greater than its children. Now having done this, we got the maximum of all elements on the root of this overall tree. So now we're going to swap the root value with the value of whatever the value is present at the current size, that is 2. Upon doing so, we finally got 7 where we wanted it to be. So now we're going to decrease our current size by 1, reduce the array, and then remove 7 from this picture. So now after doing this, we again see that the final heap tree that we formed is violating the max heap configuration. So again we're going to heapify the root. So heapify simply means that place 2 at its current position and finally make everything in a max heap configuration. So this time again 2 is checked with its children. It finds the greatest children, and the greatest child is at index 2, that is 6. So again 2 is compared with 6. It finds that 6 is greater than 2. So 6 has to bubble up and 2 has to bubble down. So when 2 comes at index 2, it again sees its children. It finds the greatest child and sees that the greatest child is 5. It compares the child with itself. It sees that 5 is greater than 2, which means again 2 will bubble down and 5 will bubble up. After doing this, again the max heap property has been restored. Now since the max heap property has been restored and we got the maximum element at the root, so we're going to swap the root with whatever is present at the current size. So we're going to swap 6 with 1. So now I got 6 where I wanted it to be. So now I will decrease the array size by 1. That is, I will reduce the current size by 1. And I'm going to remove 6 from this equation. So now again we're going to heapify the root element. So we see that we see one's children, that is 5 and 3. The greatest among them is 5. So 5 is compared with 1. It sees that 5 is greater than 1. So 5 has to bubble up and 1 has to bubble down. So now 1 comes at index 2. 1 is again checked with its children. It says that 4 is greatest, and so 4 is compared with 1. It says that 4 is greater than 1. So again 4 will bubble up, 1 will bubble down. So now we again restore the max heap property. So upon restoring this max heap property, we're gonna again swap the root value with the value of the current size. So 5 is going to get swapped with 2. So we got 5 at its desired position. So now again we're going to decrease the array size by 1, decrease current size by 1, and eliminate 5 from this picture. So now again we're going to heapify the root element. So 2 is again checked with children, 4 is greatest, so 2 gets swapped with 4. So when 2 reaches at index 2, it again sees its child. So here it has only the left child, that is 1. So it sees its child. So the child is compared with the root, that is 2. So 1 is compared with 2. It sees that 1 is not greater than 2. So there will be no more swapping, which means finally we have got the max heap configuration. Now since we have got the max heap configuration, we will swap 4 with whatever value is present at the current size index. So the current size index is index 4 and 1 is present there. So 4 is going to get swapped with 1. Now again we're going to decrease the array size by 1, decrease current size by 1, and eliminate 4 from this picture. So now our current size is 3. So again we're going to heapify the root. So 1 is checked with its child, with the children. So it sees that right child is the greatest. So 3 is again checked with the root, that is 1. So it sees that 3 is greater than 1. So 1 has to bubble down and 3 has to bubble up. So again the max heap properties has been restored. So now since the max heap property has been restored, we're going to swap the root element with the value present at the current size index. So 3 is going to get swapped with 1. So now again we're going to decrease the size of the array by 1 and eliminate 3 from this picture. So finally our current size becomes 2. So now again we're going to heapify the root element. So 1 is checked with its child, that is index 2. It says that 2 is greater than 1, so 1 has to get swapped with 2. Which means again we have converted this into a max heap. Now since we have converted this to max heap, so we're going to swap the root value with the value of the current size. So current size contains 1, so 1 is going to get swapped with 2. So we're going to remove the 2 from this equation and decrease the current size value by 1. So now that our array size has reduced to 1, so we're going to finally stop the execution here. So now let's see how to code this out the entire process. So now I'm going to declare a function called sort, and inside this function we're going to pass the parameter as max heap array. So this max heap array is actually the array that we finally printed here. So and it has a swapping code that is swaps the first element, that is the root element, with the value present at the current size. So that's what we gotta do initially, is that we have to swap the current size with that of the root value. So once we got the max heap array, that was our first step. So after the first step, we got 8 at the last and we got 1 at the front. So after this, decrease the current size value by 1. So now we're gonna have to heapify the root. So in the root, 1 is present. So we're gonna heapify the root value so that it comes at its corresponding correct position, so as to restore the max heap property. So I'm going to say that the root index is 1, and I'll call a function called move down. So I've not yet declared this function, I'm going to declare it later. So for now, it's gonna take the root index as parameter because it has to bubble down 1. It has to check with its children, whichever child is greater, it has to compare it with that of the root, and it sees that the child is greater than the root, so it has to bubble it down. So that's why the name is move down. So now I am going to declare a move down function. So now I'm going to make a call to the get max child function, and this max child function is going to return the maximum, the greatest child that the root has. So it's going to return the index of that greatest child, and we're going to store it as C index. Now let me show you how the get max child function will actually look like. So I have this function get max child, and it's going to make the index pass to it as the root. Now it calculates its corresponding left and right child. So it sees that the left child index is 2 into root and the right child index is 2 into root plus 1. So whatever is the index of the root, so 2 into that index is actually the left child index, and 2 into that index plus 1 is the right child of that index. One important property to notice is that only if the root has a left child, then only it will have a right child. If the root doesn't have a left child, so it will not have a right child. So the condition for the root to not have a left child is that the left child index falls beyond the current size index. So in that case, I'm going to write if the left child index is greater than self.current size, that is, it falls beyond the current size value, then it's simply going to return none. So if this get max child is called in the move down function, so it's simply going to return none, and C dot index will have the value of none. But if suppose left child is present, and then we can check if the right child is present or not. So if the right child is not present, then we're going to simply return the left child index. Else, if both left and right child are present, then we're going to return whichever is the greatest. So I use the max function, that is the inbuilt function Python, to give the maximum of the two values. So the first value is the value of the left child, and the second value is the value of the right child. So it passes the max value, and then it computes the index of that value. So if like suppose that if the children are 2 and 6, that is 2 is at the left and 6 is at the right, and it sees that the 6 is greatest, so the max finally passes 6, and the index will be the index of the value 6, and then it finally returns the value of that index to the move down function where the get max child function is called. So when we are heapifying this 1, which is at the root, and when we are heapifying it, it sees that which is so first the get max child returns the index of the maximum child, it will return the index of 3 to the move down function. So in the move down function, the C index becomes 3, and which means now it will see if the value present at that index is actually greater than that of the root. So if 7 is greater than 1, it will swap 1 with 7. So here I'm going to check that if C index is not none, first of all it should not be none, so it returns none when it doesn't have a left child. So when it doesn't have a left child, there's nothing swapped. So it checks if C index is not none, and if the index value, that is index value, is greater than that of the index value here, index is actually the root. So in that case, it has to swap. So now 1 gets swapped with 7. So 1 gets swapped with 7 here. So when 1 gets at 7 here, so again this 1 is going to check its children. So it sees that 3 is the greatest child, so it has to again swap with, that's 1 again gets swapped with 3 because 3 is again greater than 1. So definitely I will have to use a while loop here, and that while loop will break if in case 1 is not able to swap with any of its child. Alright, so if the root value is not able to swap itself with any of its child, that is, it's already achieved the max heap configuration, then the while loop has to break. So I'm going to declare a while loop here, and if this if condition doesn't get satisfied, that is, the root is not being able to swap itself with any of its child, that is, it has already achieved the max heap configuration, or it doesn't have a child, that is when the value return is none here. So in that case, we'll simply break the while loop. So the while loop gets broken in two conditions, that is when the value returned by C index is none, and when there are values returned by this index and there is a child corresponding to a root, but that any of the child is not greater than that of the root. So whichever case it is, swapping will not take place, and when swapping doesn't take place, this while loop will break. So in this else part, I'm going to say simply break the while loop. So in this case, when 1 has moved to index 3, so the while loop will continue, that is 1 will get swapped with 3, and then the get child index continues to run. So in this get max child function continues to run, and its get max child function, the root is the index at which 1 is present. So 1 is present at index 6, so root becomes 6. It calculates its left and right child, but it sees that its left child is none, so it returns none. Okay, so the left child index exceeds that of the kernel size. So its left child index would have been 2 into 6, that's 12. It certainly exceeds the kernel size. Therefore, this get max child function is gonna return a value of none to this move down function. So none. So it returns none here, C index contains none, and if C index is not none, then only swapping takes place, which means now C index returns none. So this if statements do not run, which means it will simply break the while loop. So now come back to the sort function in which this move down function was called. So when there is no further swapping done by the move down function, which means now again we have restored the max heap property. And remember that whenever we had restored the max heap property, we again gotta swap the root value with that of the current size value. So remember that the current size was 7. So the value at the root is 7. So 7 will be getting swapped with the value present at the current size. So 7 gets swapped with 2. And also the current size value gets decreased by 1. And by decreasing the current size value by 1, we eliminate 7 from this picture. So again, the heapification of the root element has to be done, that is the move down function has to run. So you can see that this is a while loop process. So we're gonna have to make use of a while loop, and this all will take place until our current size has finally come to the position of index 1. That is, if you remember, then when the current size index became 1, then everything was as according we wanted. So here we have to break the while loop. So if we place this everything inside a while loop, and while 1 means it is a never-ending while loop, so it will end when a particular condition is met. And that particular condition is that when the current size becomes 1, it should break. To print the output and show the result, I have added some print statements. That is, after the swapping here, it will show that self.l denotes the finally swapped list, and when we apply the move down function, then we are actually doing heapification of the root, and after heapification of the root, I'm simply printing the heapified list. So now we're going to finally call this sort function in the main, and we're going to also print the final list. And this final list printed is actually the sorted list that we want as the result. So if I save this program and we print it, you see that the initially list, that is the max heap array, was 8675431. We swapped it the first time the swapping function, this sort inside the sort function, the swapping steps took place. The swapped list becomes this, and then it gets heapified. The root value gets heapified and comes here. And similarly, you can see the rest values. The finally sorted list is actually this. So this is the final sorted list that we want. That is 1, 2, 3, 4, 5, 6, 7, 8. So you can see the result, and you can actually correlate everything step by step. Is that when the first time this gets swapped, and then the kernel size value gets reduced to 7. So initially it was 8. So kernel size value gets reduced to 7, and the array becomes this. So heapification of the root takes place, and the root comes here and 7 comes here. So after heapification has been done, the max heap property has been restored. So when the max heap property has been restored, this 7 has to be swapped with that of the kernel size, that is 2. So 7 gets swapped with 2, 7 comes here, and again the kernel size gets reduced by 1. So our reduced array is this. Again heapification of 2 takes place, and after heapification of 2, 2 comes here, and again the max heap properties has been restored, which means again swapping of 6, that is the root value, will be done with whatever value is present at the kernel size. So the value present at the kernel size is this 1. So 6 will be swapped with 1, and the kernel size value will again get decreased, again decreasing the array. So it takes place like this. You can check everything for yourself. So I hope you understood this tutorial. Like and share this video, subscribe to the channel, and thanks for watching.